Thank you for the introduction. It is my pleasure to present our work, ICthroughVR, Illuminating Cataracts through Virtual Reality, to you today. So this is a typical escape route sign. It shows the shortest route out of a building in case of an emergency. It has a certain size, is mounted at a certain height, and a certain distance to the next one. There are norms, international standards, and regulations in place that define the maximum recognition distance of such a sign. This is the distance at which you should still be able to recognize the direction the sign is pointing to. But what if you have some form of visual impairment that makes it harder or almost impossible to recognize the direction the sign is pointing to? Vision impairments affect approximately 1.3 billion people worldwide, according to the World Health Organization. The National Eye Institute of the US estimates that 26% of the US population over the age of 40 have some form of vision impairment that reduces their visual acuity and degrades their vision. This is a significant portion of the population that we should take into account when we design our cities, our buildings, our emergency sign postings, or our lighting systems. However, in architectural design and lighting design, vision impairments are hardly ever taken into account. Architects and designers simply lack the tools and the methodology to do so. With our research, we want to close this gap. We want to know, how do vision impairments affect a person's ability to see their surroundings? How do vision impairments affect maximum recognition distances of escape route signs? And how does light affect your perception under vision impairments? The question is, how can we even investigate this? Well, we could conduct a user study in the real world. But this is difficult because we would need a lot of participants with the exact same form of vision impairment in order to be able to quantify and statistically evaluate our results. This is why we took a different approach. We decided to graphically simulate vision impairments in VR. We developed a more extensive simulation of cataracts than in previous work, using eye tracking for gaze-dependent effects. We also simulated the influence of light on the visual perception of people with cataracts. And we present an improved methodology for conducting user studies in VR using participants with normal sight. And finally, we also conducted a user study in VR with our simulation. We chose to simulate cataracts because they are one of the leading causes of vision impairments. We simulate 3 different types. When you have nuclear cataract, it means that your lens is uniformly clouded. And this results in a blurred vision and therefore a reduced visual acuity. You also have a reduced contrast and a kind of yellowish, brownish vision. Through this clouding of the lens, light scatters in your eye much more than with normal vision. So light sources in your field of view can create very uncomfortable glaring effects. In addition to these symptoms, cortical cataracts create dark shadows in the periphery of your vision. And subcapsular cataracts create this dark shadow in the center of your vision. This is the virtual environment we used for our experiments. We calculated a physically plausible lighting simulation for this model of a kitchen using the light planning software Highlight, which is being developed at the VIAVIS Research Center in Vienna. We combined different effects to simulate cataract disease patterns. First, we reduced the visual acuity of the user using a depth of field effect, which leads to this blurred vision. We determine the amount of blur we need by implementing an eyesight test in VR. A common sign that is used for eyesight tests in medicine is the Landolt C, or Landolt ring, which has a gap at one of 8 possible positions. In eye exams, patients have to identify the position of this gap for different sizes of the Landolt C at a fixed distance. A person with a normal sight, for example, should be able to recognize a sign of size 6 centimeters in a 6-meter distance. If you're only able to recognize a sign of, let's say, 12 centimeters at the same distance, it means that essentially your visual acuity is reduced by 50%. So if you want to test for a certain level of reduced visual acuity, we just use the corresponding size of the Landolt ring. Building upon our previous work, we implemented this eyesight test in VR to calibrate the vision of every participant to the same level of reduced visual acuity. So we fixed the distance and the size and blur the image and stepwise increase this blur until the gap in the ring cannot be recognized anymore. Next, we reduce the contrast. We use the same methodology as for the reduced visual acuity. Only this time, instead of stepwise blurring the image, we stepwise reduce the contrast. And therefore, we are able to simulate a similar amount of contrast loss for every participant. We follow the protocol of the Pelly-Robson contrast sensitivity test, but use Landolt Cs instead of the letters like on the Pelly-Robson chart. Next, we apply a color shift, which creates this yellowish-brownish vision. And then we simulate these dark shadows of cortical or subcapsular cataracts. So this is an illustration of cataract vision with cortical cataract. On the left, you can see how this might look like with this clouded lens. And on the right, you see the lens surrounded by the iris. So this is an illustration how it might look if your pupil is wide open. But if it's a nice sunny day, your pupil would be much smaller. And therefore, less area of this darkened lens is exposed to light, which means it affects your vision less. And if you look at something really bright and your pupil is very small, you might not even notice the effects of these dark shadows at all. In order to simulate this, we need to use eye tracking to see if a user looks at bright or dark areas. And then we simply scale the texture that we use to create these dark shadows accordingly. In the final step of our effects pipeline, we simulate sensitivity to light by using a bloom effect, like you can see here in the upper left corner of the image. We also track the eyes of a user to see if they look at light sources, and then we apply the bloom effect around these light sources. In our user study, we also measured maximum recognition distances of escape route signs by placing a user in a virtual corridor where they had to advance until they could recognize the sign at the end of the corridor. We tested this with clear vision and also with all our 3 different types of simulated cataracts. The ring that you can see here marks the field of view that you can actually see in the headset, which is much smaller than what's actually rendered. The results of our user study show that cataract vision reduces your maximum recognition distance of escape route signs significantly. And you can find a more detailed discussion of these results in the paper. We also tested different lighting configurations in our virtual environment. So we had this 3D kitchen with 2 different lighting setups, And we let our users test both lighting setups with all 3 types of cataracts. And then we ask them if they like the first one or the second one better in terms of perception. And the results show that users did not like the second lighting system because there were a lot of spotlights beneath the kitchen cupboards that were most of the time in your field of view and created a lot of uncomfortable glaring effects. So to conclude, we demonstrated that eye tracking can be used to simulate gaze-dependent effects in VR. Our implementation is not as fast as it should be. So you experience a noticeable lag of the eye tracker. But our participants reported that they get a better understanding of these eye diseases with the eye tracking than without. We have shown that it is possible to calibrate different symptoms to a similar level of severity for all users. And we showed that multiple effects can be combined to simulate different cataract disease patterns. Our user study showed that cataracts reduce the maximum recognition distance of escape route signs significantly, and that lighting systems with many light sources in the field of view of the user are perceived as especially uncomfortable. Therefore, we recommend investigating the use of passive lighting for people with cataracts. And with this, I would like to thank you for your attention, and I'm happy to answer any questions.
Thank you very much. I will get started with a question. So how easy is it to transfer the system that you've created for simulating cataracts to a novel scene? So let's say I've built a virtual environment and I want to see how it looks to someone with cataracts. Is it as easy as installing a Unity package, or do I have to do something manual in order to make it work?
We implemented this in Unreal. So basically, all you'd have to do is import the scene to Unreal, and you're good to go.
Oh, fantastic.
Hi, Christoph Schulz from the University of Stuttgart. Did you actually try to validate your simulation using photographs of lenses or something like that?
No, we were working together with an ophthalmologist. So we used her expert knowledge to create our simulation. And we had a constant feedback loop, always talking to her, asking how her patients perceive these type of vision impairments. And we sent her pictures and videos. And we would like to also test our simulation with patients in future work. So there is cataract surgery where basically this clouded lens can be removed and replaced by an artificial one. So it would be very interesting for us to have user study participants who used to have cataracts and have them then try our simulation and evaluate it. But yeah, this is going to be future work.
So you might even also get lenses that are clouded and measure them sort of after they're removed from the patient?
I don't think so, because in the process of removing them, they are destroyed as far as I know.
Okay, thanks.
Hello, my name is Kojiro from Osaka Institute of Technology. I wondered, have you actually validated, the thing is, you can try and test a variety of virtual room settings to see what is the best condition for cataract patients. But did you actually transfer that finding into the real room and modify the lighting to see whether your finding in virtual environment is applicable to the real environment?
We did not do that yet, but we definitely plan to do so.
Okay, thank you very much.